Hello, chemistry. Today, a short summary slash review slash explanation of the concept of enthalpy as it relates to state changes. And so specifically, we're going to call these the enthalpies of fusion, which is related to the solid liquid state change boundary, and the enthalpy of vaporization, which is related to the liquid to gas state change boundary. So enthalpy is um, sort of as a review and expansion of what we already talked about in class, is the energy of structure. Now, this little equation here, I'm not going to expect you to memorize this. This is something that gets studied a little bit more in physics. Well, I guess it's chemistry or physics. But enthalpy is the term H. So believe it or not, enthalpy is H and E is something else. But the H relates to the idea that enthalpy is also sometimes just described using the word heat. So what we're really talking about is the overall internal energy of the substance, which is really what E means. So that could be inter and intra-particle attractions. And then this factor that is pressure and volume. So that's your P and V. So the overall enthalpy is a function of the internal energy plus this pressure volume factor. And that kind of ties into what we've talked about with state changes, as state changes are a function of energy and of pressure. And then there's a couple different ways that we measure energy, and that can be with temperature, and that can also be with the interparticle attractions. So in terms of physical changes, in terms of state changes, the enthalpy really is the energy of the structure. So for a specific substance, let's take, for example, water, that is kind of our standard example. A solid has a lower structural energy than a liquid, and a liquid has a lower structural energy than a gas. So in order to go from solid to liquid, you have to put in some energy specifically to change the structure. In order to go from a liquid to a gas, you have to put in energy specifically to change the structure. And that energy falls under the overall heading of enthalpy. So state changes are due to a change in enthalpy, and that is related to the interparticle structure. So the forces that occur from one atom or one molecule of a substance to a next. We're not talking anything about the chemical bonds when we talk about state changes. It's purely a physical process. So state changes will occur at specific conditions for a substance. So we know these as the points: melting point, freezing point. And so the melting point is a function of temperature and pressure. The boiling point is a function of temperature and pressure. Vaporization is a function of temperature and pressure, and also those are related to vapor pressure. But that particular set of conditions where the state change will occur gets the name of a point: melting point, freezing point, sublimation point. And we saw that on the phase diagrams that we did, that we could map out for conditions of temperature and pressure what the boiling and melting and sublimation and deposition and condensation and freezing points would ultimately be. So the strength of the interparticle attractions for a substance is constant. That's important to remember. When we talk about a state change, we're not talking about a change in the strength of the interparticle attraction. The strength of the interparticle attraction is defined by the internal bonding. So ionic bonds tend to have a different strength than covalent bonds. Polar covalents tend to be different from nonpolar covalents. Even within polar covalent bonding, the shape and the layout of the poles makes a difference in terms of interparticle attraction strength. Water has that 104.5 degree angle and the very well exposed poles, so that has a particular set of effects. That does not change for a substance. What changes is how those interparticle attractions are or are not able to keep the particles in a particular structure. And the analogy that I did to this and talked about in class is, trying to hold on to somebody else, trying to hold on to somebody else's hand while you're sitting still versus walking versus running. That, yes, the speed of the particles affects that ability to hold on to keep the attraction together, but it's not like it's easy to hold on to somebody's hand when you're sitting still, but when you're at full sprint, it's a little bit harder. And it's not because your arm is somehow weaker. It's just that the strength of your hand makes it more difficult to maintain that connection. So temperature and pressure affect the ability of those attractions to maintain structure, but they don't actually change the attractions. The interparticle strength for a particular substance is constant as long as you keep the same substance. So when we're changing enthalpy, we bring in that great mathematical little symbol delta. So when we talk about a change of enthalpy, we talk about a delta H. So H for enthalpy, delta for change. So going from solid to liquid, there will be a particular delta H that has to occur for a substance. And going from liquid to a gas, there will have to be a particular value of delta H, an amount of energy per amount of substance that has to go in to cause that restructuring to occur. So here's a typical little melting vaporization curve. Remember that if we showed this for condensing and freezing, it would be the same thing, just going the other way. But at the melting and freezing point, so again, the melting and freezing point is going to be at a particular temperature, assuming you're keeping a constant pressure. I got to just keep reinforcing that when I say this, that melting and freezing points and boiling and condensation points are a function of pressure. Vaporization, much more of a function of pressure than melting. Normally, the pressure effect on melting is fairly minimal, almost negligible in most cases, but pressure has a huge effect, as we saw with water in the vacuum chamber, on boiling point. So for this discussion, we're going to assume that we're doing this in the lab and we're maintaining constant pressure. So at the melting or freezing point temperature, we call that amount of enthalpy to induce the state change the enthalpy of fusion, also called the heat of fusion. Again, the terms enthalpy and heat are often used interchangeably. So the flat part of this curve here, where it says melting, that's the time during which the substance is absorbing, in this case, the heat of fusion. So the temperature heats up, so where the particles are speeding up, because temperature is a measure of the motion of particles, their kinetic energy, and then the particles reach a point where they can't speed up anymore and maintain their structure. So then they start absorbing the heat of fusion, and once all the particles have absorbed that heat of fusion and they've restructured themselves, then they can go back to speeding up again in the liquid state. So melting, the substance has to gain the heat of fusion. So notice subscripts is something to really learn about science, in that when you have multiple things you're talking about, so if you have a whole bunch of different temperatures you're talking about, or a whole bunch of different forces, or a whole bunch of different enthalpies, we use a subscript to tell us which one we're talking about. And for enthalpy of fusion, we usually use the three-letter abbreviation FUS to represent that. So at melting, you're absorbing, adding in the heat of fusion. At freezing, you're losing it. So same thing, opposite direction. So one is adding, one is taking away. Sometimes at the freezing point, it gets called, instead of negative delta H of fusion, it's called the delta H of solidification. But maybe half the time I ever see that. Most of the time you just talk about a negative delta H of fusion. It really reinforces the point that heat of fusion is one value. It's a particular value for a substance, and the only thing is do you add it or take it away depending on whether you're heating or cooling. At the boiling and condensation point, that's called the heat of vaporization, or the enthalpy of vaporization. Again, it can also be called the heat of condensation. That one I maybe hear a little bit more frequently, particularly in weather, when they talk about the formation of fog, or particularly when the forecasters are trying to talk about whether or not it's going to snow or rain in one of these winter storms. That is, the water falls from the sky and it begins to evaporate. That evaporation process absorbs energy, and that can actually make it colder and change rain to snow. There's all sorts of applications with that go on. I really like atmospheric processes are really cool to me, and I studied some of that in college. And my retirement gig after I'm done teaching is I think I want to become a weather forecaster for a NASCAR team. But that's a completely different subject. Um, so heat of vaporization, heat of condensation, and again, if you're vaporizing, then that is adding in the delta H vap. So again, the abbreviation for vaporization is VAP. And then if you're condensing, then the substance has to release or give off or lose the enthalpy of vaporization. So one thing to remember is under normal conditions, I can't say always again because pressure can play such a significant role in this, but under normal conditions, normal atmospheric pressure for substances, the heat of vaporization is going to be greater, usually significantly greater than the heat of fusion. And if you look at this graph, you'll see that the length of the line with energy being on the x-axis, which could be the time you have it sitting on a hot plate. But the length of the plateau here for vaporization is significantly longer than melting. And that's because, as we've said before, gases are a lot different than solids and liquids. Solids have interparticle attraction that holds things together. Liquids have interparticle attraction that holds things together a little bit more loosely than a solid, but they still have some type of interparticle connection that's being maintained. In a gas, that's gone. So it takes a little more effort in order to get that to spread apart. So kind of the overall example of this, the analogy I came up with is, I'm sitting here in my chair recording this video, drinking a little bit of coffee, as I often do. And so as I'm drinking coffee, as I'm taking in caffeine, and in this case, a little bit of sugar, I get a little bit more energetic, a little bit jittery. I have my chair that I can swing back and forth on. But as I take that in, eventually it's like I can't sit still anymore. So I want to walk around the house. So to go from, wiggling in my chair in my fixed position to moving around the house, I have to do some work. I have to get up from my chair. So getting up from the chair, that extra work that has to be done to change me from being locked in this spot to being able to kind of wiggle around within the boundaries of the house, that getting up from the chair would be absorbing the enthalpy of fusion. If I continue to get more energy, whatever, I decide to go out and, eat a box of cookies or something else I shouldn't be doing, and all of a sudden, like, oh, I want to go for a run. So then if I'm going to go outside and it's like 25 degrees outside and I'm going to go for a run, I need to put my shoes on, I need to put a jacket on, and I maybe want to get some earmuffs on, and I want to get my AirPods and I want to listen to some music. I have to do all of those extra things to then go out and go for a run. So whereas it just took me a little bit of effort to get out of my chair to walk around the house, I have to do more things to go out inside, although the conditions outside, whether it's winter, spring, or summer, might change the amount of effort that it takes for me to get ready to go out and go for a run. So that would represent the pressure that is affecting how easy or difficult it is for me to leave the confines of the house and go out and essentially be that running around gas particle. So movement is temperature, structure is enthalpy. And because it takes more work to become a gas, under normal conditions, we usually see a plateau on the graph that is much longer in the vaporization process than it is in the melting process. As far as sublimation and deposition, we've kind of left these two out. Something to keep in mind, so reminder, sublimation is solid directly to gas, and deposition is gas directly to solid. Sublimation is just melting plus boiling. Deposition is just condensation plus freezing. So every state change is the same thing, just opposite direction. So even though you're going directly from solid to a gas, mathematically you're going solid, liquid, gas. So the heat of sublimation, as it's called, is just adding in the sum of the heat of vaporization and the heat of fusion. Therefore, the heat of deposition, or the enthalpy of deposition, is just losing. Oh, that should be a different sign. Sorry, that's a typo right here. Make this a plus sign right here. Hopefully you can see my cursor, but that should be delta HVAP plus delta H of fusion. So heat of deposition is just losing the same quantity. And so I brought in my little scarecrow here as the example I try to do in class from The Wizard of Oz, that sublimation and deposition are the same thing, just opposite directions. And the way we say that is all state change processes are perfectly reversible. Same thing, opposite directions, is just whether you're taking in something or giving up something. And that means that pure substances, this entire process has been talking about pure substances. Mixtures, as we looked at with salt water and freezing point depression, all these other things that happen, it gets a lot more complicated. But for a pure substance, if you take it and you heat it or you melt it, you boil it, you do these various things with it, and you take careful observations on those changes, you can identify the substance, or at least you can narrow it down to specific substances based on those behaviors. And that was something that in our Percy Julian story, one of his critical experiments was proving that he had created a particular substance by running a melting point test. We've done that in the lab or through the lab videos for identifying some substances that we did with melting and freezing in the lab. So that becomes one of those kind of textbook lookup things of at what temperatures and what situations and what energies does this substance undergo the restructuring from one state to another. I'm going to switch over to another source now. So quick stopping point here, and then I'm going to talk you through some heating and cooling graphs, and then we'll wrap this up. All right, so I've switched sources over to my Notability app here. So this is the same presentation that we went through, and we ended up here after Mr. Scarecrow and said that we were going to look at some examples of heating and cooling graphs. I'm going to zoom this in a little bit. So there's some different ways that these are presented. Sometimes they're presented with temperature on the x-axis and energy on the y-axis. And in that case, you would see something that looked like this, where they would be kind of vertical, vertical cliffs, I guess, instead of plateaus. But again, we're seeing periods of time where the substance is being heated and changing temperature, and then the temperature stops changing. And so this first temperature change, that would be your enthalpy of fusion, and the second change would be your enthalpy of vaporization. But in any case, during the time when a substance is restructuring itself, the temperature does not change. So you may see those, but I'll keep it just for consistency here with what we did in the lab. And so in the lab, we would create a graph where this is temperature, and then the x-axis sometimes is time. And remember that over time, we're just changing energy. So if energy is increasing, then that is heating. And if energy is decreasing, that is cooling. So in our lab, we did both. We put things on the burner or on the hot plate, and we heated it up, and then we allowed it to cool. So if we take this through a typical situation, so I have a substance here that is in the solid state, and I add energy, it's going to warm up. And it's going to warm up until it reaches a point where it cannot maintain the solid state at that set of conditions. So this temperature here would be what we call the melting point. I'm just going to abbreviate MP. So it's a temperature value, and then it's going to undergo its state change. So this is the process where we'd start to see some of the solid beginning to melt. This is the process at which we'd finish seeing it melt. The trick in the lab is that the temperature sensor may have been measuring liquid, or it may have been measuring solid. So as soon as the substance turns to liquid, that liquid can then continue to heat. So keep in mind that temperature is the average kinetic energy in a substance. And when you have a sample that is part liquid, part solid, the kinetic energies are not going to be even throughout that substance. So when you look at the when you look at the, well, what am I trying to say? When you look at your physical observations of state changing, that may not be as accurate as the temperature data of state change would be in terms of melting point, freezing point. So the substance warms up, it reaches a point where it's going to start absorbing energy. And this amount of energy it has to absorb is going to be the heat of fusion. And so it's absorbing it. It's then going to continue to heat up once it's fully melted. It's going to reach a point where it begins to vaporize, and we would expect that plateau, assuming we're heating at the same rate on the same hot plate, that we would expect that to be a bit longer of a plateau, and then this temperature at which that occurs would be the boiling point. And once it's fully a gas, if you could somehow capture and heat that gas, you could continue to heat it. And eventually, you could probably heat this till a point that it starts to ionize and it would have plasma, but we won't go there. If I turn this around and I go the other direction, so I'm going to start my timer over again, and we start here where we left off. So this is going to be in the gas state, and I begin to cool it. I'm going to reach a point where the particles can no longer slow down and be free of each other's interparticle attractions. So then we are going to give off the enthalpy of vaporization. And if I've done this right, the length of this line should be pretty much equal to the length of that line, assuming we're cooling at exactly the same rate that we're heating. The reason the length of those lines might be different is if you're heating or cooling at a different rate, but the actual amount of energy would be the same. Once it's fully condensed, then it can continue to cool off. And then once it reaches a point where the particles have to structure themselves in a more rigid manner because they're going so slow, it would undergo a point where now it's losing the heat of fusion. Once it's fully, and I guess I drew that line a little bit too long, because it should be the same length as the other one, assuming that we're cooling at the same rate we're heating. Once it's fully solidified, then it can continue to cool off. So the sloped segments are where motion is changing. The plateaus, or the horizontal segments, are where structure is changing. Temperature, enthalpy, pressure all have this interrelationship in describing the overall state of matter for a substance, a physical characteristic of pure substances.